Okay. Now, let us go to the cyclohexane disubstituted cyclohexane, where the substituents are in the 1-2 relationship. Okay. And we will take the simplest case 1,2 dimethyl cyclohexane, 1,2 dimethyl cyclohexane. Okay. Now, what now here is a, when you come to this 1,2 system or 1,3 system, there is this question of stereoisomerism, the real stereoisomerism, not the conformational, the stereoisomerism which were classified as diastereomers. So, now you have a case of diastereomerism, not the conformational diastereomerism, but the diastereomerism where the diastereomers cannot be interconverted by rotation. That situation arises here. How? Like what are diastereomers? We know that like cis and trans butene, they are diastereomers and they cannot be interconverted by rotation. You have to break the bond and then make the bond to convert one from the other. Okay. So, they are diastereomers. These are called cis and trans. Similarly, in 1,3 disubstituted 1,2 or it is 1,3 or 1,4 in disubstituted system, not the 1,1, when it is 1,2, 1,3 and 1,4, what happens? Because the substituents can have alpha or beta orientation. So, you have different possibilities, like if there are suppose an X group and then an Y group. Suppose the relationship between X and Y, not in terms of axial equatorial, in terms of alpha beta, in this form you see both are beta. So, if both the substituents occupy the same facial relationship, means if both are beta or both are alpha, then that is called a cis isomer. On the other hand, if one substituent is beta, another is alpha or vice versa, that is called the trans isomer. Okay. So, that is the first step. So, in 1,2 dimethyl cyclohexane, that can exist in cis form or in the trans form. Okay. So, we have to separately consider these two forms. So, first take the cis form. Okay. Now, what is the cis form? In just the planar formula, if I write it in this hexagonal formula, it is not having this type of conformation, but just for simplicity, let us first draw the hexagon. And what is the cis compound? That is cis dimethyl cyclohexane, 1,2 dimethyl cyclohexane. See, if I put one methyl beta, then I have to put the other methyl also in the beta orientation. Okay. I could have done the opposite one, this could be alpha, then that is alpha. So, this is the cis isomer. Okay. Now, this is not the conformation, because this is the planar hexagon, that is we know that it does not exist in the plane hexagon formula structure. So, what it does, you have to draw now and convert it into the chair form. So, convert it into the chair form. Suppose this is your 1 carbon, this is your 2 carbon, 3, 4, 5, 6. So, suppose this is 1, this is 2, this is 3, 4, 5, 6. Now, at 1 you have the methyl and which is beta. Now, you know at 1 there are two substituents, one is axial, another is equatorial, but the equatorial is in the alpha form and the axial is in the beta form. So, this methyl has to be put in the axial orientation. So, first you consider the alpha beta nature and then accordingly you place it in the axial or equatorial position. So, methyl will be equatorial and the hydrogen methyl will be axial and the hydrogen will be equatorial at C1. At C2 you have to now place you have two bonds equatorial and axial. At C2 what will happen, because the methyl is beta, so you have to place it in this position and this is the hydrogen. So, that is one conformation. This conformation, one methyl is axial, another methyl is equatorial. Okay. So, if you flip this molecule, the energy will not be different at all, because again you have the similar situation, one methyl will be axial, another methyl will be equatorial. Remember, in flipping, axial becomes equatorial, equatorial becomes axial, but alpha remains alpha, beta remains beta. So, now in flipping, this C1 you have brought down, C4 you have brought up. So, this is 4, this is 1, 1, 2, 3, 4, 5, 6. So, at C1 you have the methyl which was earlier axial, now it will be equatorial. And at C2 you have this beta equatorial. So, now that will be beta axial. Okay. Both have equal energy because in both there is one axial methyl, there is one equatorial methyl. But for suppose just for sake of problem, if I ask that how much extra energy now this has over a cyclohexane chair. In a cyclohexane chair we have already calculated that was 5.46 butane units, and those 6 butane units were in the gauche conformation. So, in this case if I ask that how much extra energy you have now incorporated into this system by putting these methyl groups in a cis fashion, okay, one axial, another equatorial. So, what you have to do? You have to calculate again the number of butane units that you have incorporated by putting these two methyl groups. Okay. Now, what are the butane units? We know that if we attach one carbon to a cyclohexane, you incorporate immediately two additional butane units. Okay. One is this, another is this. We also know one more thing, that if the substituent, if the carbon is axial, then these two butane units are in the gauche conformation. And if the carbon is in the equatorial position, you introduce the butane units, but these butane units are in the anti. So, equatorial carbon does not give any extra energy. Okay. Now, let us try to do that way, that this is one carbon which you have attached to this C1. So, what you have done? You have incorporated two extra butane units, one is this, another is this. Okay. And for this carbon you have introduced two extra butane units. What are those? Those are, this is the methyl. So, one is this one, another is this one. Okay. This I can write it methyl 1,6,5, methyl 1,2,3, that is for this carbon, and then we have methyl 2,3,4 and then methyl 2,1,6. Okay. But that is not the end of the story. There is one more extra thing that is there, and that should not escape our eye, and that is because these methyls are in the 1,2 position. So, now they themselves form a butane unit, and that is this one, maybe the white chalk will show. So, an extra butane unit is there, and that is because they are placed in a 1,2 fashion. So, number of extra butane units in this form is 6 is already there in the cyclohexane, but the excess. So, 6 plus, now the plus is, now you have 5 butane units, 2 for each carbon atom that you have introduced, and another is the mutual butane unit formed, the butane unit formed due to their mutual relationship, the 1,2 relationship. So, you have 5 butane units, but out of these 5 now you have to find out how many are gauche and how many are anti. So, out of these 5, because this is axial, so axial will introduce 2 gauche butane. So, out of these 5, if you break down these 5, so out of these 2 are from this axial methyl, they are in the gauche form, and equatorial methyl does not introduce any extra energy because they are in the anti form. So, these 2 are in the anti, but the mutual one, this one is another gauche form. Okay. So, 2 in the gauche unit, 1 is in the gauche, that is the mutual, and the rest 2 are in the anti. I hope this is clear. So, this does not, these are the anti, these are the gauche, and the mutual one is also in the gauche form. So, the extra energy that you have is extra energy over a cyclohexane is 2 plus 1, that means 3 into 0.9. So, 2.7 kilocalorie per mole. Okay. So, that is clear. Now, this mutual relationship will not be there if they are in the 1-3 position. This happens because they are in the 1-2, they are having a 1-2 relationship. Okay. The next question that comes, that is also very interesting, that what is this molecule chiral? Chirality, we have not described the chirality yet, because in 1-1 system there is no question of chirality, because when you have two different groups, even if you have two different groups, there will be a plane of symmetry going through this carbon and this fourth carbon. C1, C4 will form a plane which is a plane of symmetry for this molecule. So, 1-1 will not be chiral, but once you have this 1-2, 1-3 system, then this sort of chirality issues also come, that whether this molecule is chiral or not. Okay. That is little bit tricky, because what happens, how to check chirality of a molecule? Either you can see whether there is any symmetry present in the molecule or not, that is one way. The other way, you draw the mirror image and try to see whether they superimpose or not. Okay. Now, interestingly, if you draw this molecule in the cyclohexane as a planar hexagon, you will immediately see that it appears that it has got a plane of symmetry, if you draw it in this fashion. But in the actual conformation, this is axial, that is equatorial. So, there is no plane of symmetry. Okay. So, in the actual, this is the conformer. So, actual conformer does not have any plane of symmetry. Okay. So, the question is, now there is a, this plane of symmetry is gone. So, the question is, now is it chiral? So, how to answer that? So, you draw the mirror image of this, because it will be difficult to inspect all sorts of symmetry elements in this type of system, because you may miss a symmetry element by doing so. So, better draw the mirror image, and if you draw the mirror image and then try to see whether they are same or not. Okay. So, what will happen in the mirror image chair has to be the mirror image, and then put the groups. So, this methyl will be here and the other methyl will be on this side. Okay. So, this is the picture, the mirror image. Now, the question is, are they superimposable? What is the relationship between these two? Are they superimposable or not? Now, this is how to answer this type of question, that relationship between different chair forms, the same molecule written in different types of ways. So, whether these are same or they are not same, how to decide on that. Okay. Now, there are again different ways. Today, I will give you again a mnemonic device by which you can compare this versus this. The best way of comparing this and that is to try to turn it around. This is the problem, is you cannot directly say whether these are two are same or not, because the problem is on this left side are the methyls and here on the right side are the methyls. So, either you now start rotating it and try to bring the methyls in the respective positions which are here, and then see whether they are same or not. Okay. Now, that is one way, maybe next time I will do that. Today, I will give you just a mnemonic device. Mnemonic device is that will quickly solve this issue, that whether they are same or not. That device depends, see, that relies on the relationship between these two methyls. So, I can have different types of relationship between the methyls. I can check whether they are axial or equatorial, what is their status. I can check whether they are alpha or beta, that status I can check. And another thing I just incorporate, that is that I decide to traverse through these carbon chains and come back to 1. That means, I start walking from here, go to C2, the minimum, that is that the, because I could have gone the other way around also, but I want the carbon which is having the substituent to come very quickly. So, I start walking from C1, then come to C2, then C3, then C4, then C5, then C6 and come back to 1. Okay. So, I do this walking across the ring system in both the molecules. Okay. And then see. So, that means, I have now 3 parameters. One is, as I said, axial equatorial nature of the substituent, the other is the alpha beta nature of the substituent, and a third parameter I am introducing, that I am trying to go from 1, then 2 to 3 to 4. So, I want to traverse through the ring in such a way that the substituents come very quickly, because I could have gone, again I repeat, I could have gone this way, but that way the first I go to a unsubstituted carbon, then another unsubstituted, then unsubstituted, then unsubstituted, then the substituted one. Rather than doing so, what I do, I decided to walk in such a way, traverse in such a way that the substituted carbons come very quickly, okay, the shortest path in that sense. So, I have a direction. See, when I come from this to that and then traverse like this, I have a directionality now, because whether it is clockwise or anti-clockwise. So, if I have these 3 parameters and then write those parameters and then have the same 3 parameters here and then compare them. Okay. An example will make it very clear. Suppose I decide that I come from this axial, I start from here, that means, I come from this axial methyl and go to the equatorial methyl. So, this way 1, then 2, then 3, then 4, then 5 and 6. So, I fix this axial to equatorial motion. So, I come from axial to equatorial, I could have done the other way around, but suppose I fix it that I go from this axial methyl to the equatorial methyl and finally, then C3, C4, C5, C6. So, how are they behaving, means in terms of facial relationship? I am going from a beta methyl to a beta methyl, okay, a beta beta relationship. And what is my direction? If I do that, I am actually traversing in a clockwise fashion. I am traversing in a clockwise fashion. Okay. So, the direction is clockwise. Clockwise rotation. Okay. I do the same thing here, okay. But I fix the first one, I do not change the first one, axial to equatorial. So, if I want to move from an axial methyl to equatorial methyl, I have to start from this position and then come back to the equatorial methyl, and I see these 3 parameters. So, axial to equatorial I go, and then I see that what is the facial relationship. This is beta and this is also beta. So, the first 2 are same. So, what is different is that I now traverse in an anti-clockwise direction. I traverse in an anti-clockwise direction. Okay. Now, out of these 3, this will always be the same, because that is the first parameter I fix. I do not change that parameter, axial to equatorial, that parameter I fix. So, that is fixed. Then I compare these 2. I compare these 2. If I see that there is one difference here, there is only one difference, anti-clockwise, that is clockwise, then these 2 are not same, they are mirror images of each other. And if I see that both are, all these 2 are same, that means all 3 are same, then they are same molecules. Okay. And if I see that these 2 are both different, see there are 3 scenarios, because this I have already fixed, axial equatorial. So, I have 2 more parameters. If both the parameters are same, then the molecules are same. If one of the parameter is different, then they are mirror images of each other. If both the parameters are different, then again it come back to the original situation, that means both the molecules are same. See, both are different, then both the molecules are same. So, these type of 3 scenarios can come. Here we are seeing only one difference, this is anti-clockwise, that is clockwise. So, they are not superimposable to each other, they are different. So, they are non-superimposable, Okay. So, according to the definition of chirality, this molecule is chiral because it shows a mirror image which is not same with the original. So, this molecule is chiral, but nobody is yet to separate these two molecules. Why? Because when you flip this molecule, see, we have just checked the relationship between the mirror image and the original one. Now, the question is, when you flip this, what happens, whether this remains the same with this or this becomes same with the mirror image or not. So, we have to again put these three parameters and check. So, I start from an axial to equatorial methyl, that journey axial to equatorial, and then it is beta to beta, and this is the direction is again anti-clockwise. So, basically what is happening now? This is suppose my original A, this is my flipped form B, and this is the mirror image C. Okay. I know that this should be chiral because the mirror image is different, but however, there is a problem. Now, the flipped form becomes same as the mirror image. So, if the flipped form becomes same as the mirror image, and since both these two have same energy, because one axial, one equatorial situation. So, in a mixture, if you try to isolate this molecule, half of this will flip and go into the mirror image. That means, this molecule will always exist as a 50-50 mixture of the two forms, the mirror image and the original. Why they are remaining 50-50? Because they have the same energy and they are obtained, they are interconvertible by flipping. So, this is what is called now non-resolvable, a case of what is called a non-resolvable DL pair, non-resolvable DL pair. So, if someone asks that what is the, if is cis 1,2-dimethyl cyclohexane chiral? Yes, it is chiral definitely, because according to the definition of chirality, mirror images are not same. Okay. But you cannot separate these two, because by flipping this is converted to this one, that I have already shown by this mnemonic device. Next time I will do the rotation, that by rotation how can you really prove that by that means the other way around I can say that when I flip this, it goes into the mirror image. When I flip this molecule, it goes into the mirror image, because the mirror image has been proved to be identical with this one. Okay. So, do not get confused, again I can simplify a little bit. This is the original molecule. If I flip it, the flipped form is the mirror image of this one. Okay. So, I do not have to draw the mirror image, this is the mirror image, and these two are present in 50-50 mixture, and this because they have the same energy and the energy barrier is very low. So, it is you cannot separate these into individual isomers. Okay. So, that is why we say that it is existing as a non-resolvable DL pair. If you go by the planar conformation, that means the hexagon, this type of conclusion you cannot reach, because planar conformation says that it is a mesoform, because it has got a plane of symmetry, but that is not correct. It is not a mesoform. See, initially people tried to measure the optical activity, the rotation, but they never got the rotation out of this. So, they thought that meso is all right, that they are saying it is meso means no optical activity, but that is wrong. This is not meso, that is non-resolvable DL pair. The reason it does not show any optical activity is because you cannot separate these two. Maybe at very low temperature it is possible, and one day will come when people will isolate these at very low temperature and separate them. Okay. But the question is basically we are talking about the room temperature chemistry, that at room temperature under ambient condition, what happens? You cannot separate them, they exist as a non-resolvable DL pair. That is for the cis compound. Okay. for the trans compound, again I first draw the planar formula. This is the trans one. So, if you write in the cyclohexane chair form, suppose this is the 1 carbon, this is the 2, and C1, because it is beta. So, you have to put the methyl in the axial position, and you have to put the other methyl alpha, that also in the axial position. So, this is one form. If you flip it, you get the mirror image chair, but you gain something. And what is that? Now, both the methyls, so this is the number 1 methyl 2. So, 1 is here now. So, methyl is here and the 2 methyl is here. So, both the methyls are now occupying equatorial positions. So, it is a di-equatorial system and this is a diaxial system. So, it will be mostly almost 100%, close to 100% in this di-equatorial form. Why? Because you can say that the rule of thumb that the groups do not occupy the axial position, because there is 1,3 diaxial interaction. So, when you put the methyl in the axial position, so you have how many diaxial interactions here, and then one is for this up methyl and the other is for the down methyl. That is one way of explaining the instability of this, because it suffers from this 2 here 4 interactions, methyl hydrogen diaxial interactions, which is not present here. Okay. The other way, you can again start calculating the number of extra butane units that you incorporate and what is their status. Okay. What is their status? And see, extra butane units will be again 5, because for each carbon you are introducing 2 butane units and then their mutual relationship, that also constitutes one more butane unit, that we have seen in the Sis form. So, now what is the energy difference between this and that? In the Sis form there was no energy difference because one was axial, another was equatorial. Here this is diaxial, this is di-equatorial. So, what is the energy difference between the two? So, that will rely on the butane units, what is the status of the butane units. So, this is axial. So, that will immediately put 2 gauche butane units. This is also axial, that will immediately put 2 butane units, 2 gauche butane units. Okay. So, these 2 axial methyls have 4 gauche butane units interactions, and the mutual one, interestingly, fortunately the mutual ones are in the anti form. So, the other one is anti. In the case of Sis form, in the case of di-equatorial form, this is equatorial. So, that extra butane units, these are all anti. So, this is anti. For the equatorial methyls, you do not have, you have all anti, but the mutual one, the question is what happens to the mutual ones. I can show you what happens to the mutual ones. See, this is the diaxial form, this is axial, that is axial, and what is the di-equatorial form? That you flip it, take this up and take this down. So, this is the di-equatorial form, this is equatorial, that is equatorial. What is the relationship between this di-equatorial? So, look at these, the dihedral angle is 60 degree. So, the mutual butane unit is having a 60 degree dihedral angle. So, that constitutes 1 gauche butane unit, okay, plus 4 anti, and that is due to the incorporation of equatorial methyl, that is the normal. The mutual one is the gauche. So, the difference in energy between these two is what? Will be 3 gauche butane interactions. So, that means 3 into 0.9. So, that is 2.7. Okay. And that is the correct way of looking at it. See, if you look at the See, we are calculating on the basis of this 1,3 diaxial interaction and we landed up having 4, but here if you do it correctly as the butane units. So, ultimately the difference comes to be 2.7 kilocalorie per mole. Okay. And regarding optical activity, now there is this flipping is almost stopped because this is not present. So, you have only this and you can draw the mirror image the way I said. You can draw the mirror image and the mirror image will not be identical, the mirror image is non superimposable, and in this case flipping does not give you the mirror image. So, it will be present as a resolvable DL pair. It will be present as a resolvable DL pair. Okay. I think next day we will start turning this molecule and what is the perspective projection formula. If you turn it to 60 degree, then 120 degree and where are the positions of the methyls, because that way that is the very basic ab initio approach to compare between two cyclohexane rings. Okay. The way I did it is a kind of mnemonic device just to help you out in sorting out this type of problem, that directionality, alpha beta nature and the axial equatorial nature. Okay. So, that part we will do the next time and we will also cover the 1,3 and 1,4 disubstituted systems. Thank you.